determine whether the series ln of n over n converges or diverges. So, when I have no idea, I don't recognize this as a geometric, I don't recognize it as telescoping. Remember, I always start, what did I start with last time? The divergence test. So let's start there. So I'm going to calculate the limit as n goes to infinity, ln of n over n. What am I going to get for that? Infinity over infinity. What do we use when we think of infinity over infinity? L'Hopital's rule. But I got to change this, right, into a function first because I got to take derivatives, so I need to replace n by x. Okay, and now we're going to take and use L'Hopital's rule. So what's the derivative of ln of x? 1 over x, the derivative of x, 1. So I'm really just looking at the limit as x goes to infinity of 1 over x. That's the 0, right? 0 for that limit. What happens when I'm using the divergence test and I get 0? It's inconclusive, right? If I get anything other than 0, I can say that the series diverges, but here I got 0. So remember, anytime you get 0, my divergence test is inconclusive, which means we've got to try something else now, okay? So that's something else. We don't know a lot. Yep.
It's inconclusive to the divergence test. We already know it's not divergence. Why do we go?
It doesn't tell you that it's not divergent. Inconclusive means you have no result. Okay. The divergence test only tells you that something diverges. That's why it says divergence in the name. It only tells you something diverges. It doesn't tell you that something converges. Yeah. Yeah, which is why it's not helpful all the time. It's only helpful if your series happens to diverge and the limit is not 0. Yeah. Okay, so we don't have a lot of other tools right now. We only have the integral test. So we're gonna, right, use the integral test here. I convert this into a function. What things do I need to check in order to use the integral test? We said in all of our examples last time, we needed positive, continuous, what was the other? Decreasing, the other thing, okay? Well, it's not too hard to see that this is going to be continuous and positive on our interval from 1 to infinity. It's made up of continuous functions. The ln of x and x are both continuous. The denominator is never 0. The numerator and denominator are positive. The only difficult part is showing it's decreasing. Right? How do we show a function? Take the derivative. Okay, f prime of x. So what's the derivative of that function? All over x squared. Yep. So let's simplify that. 1 minus ln of x over x squared.
It'd be negative because that 1 over x cancel out with the x, so you have a negative one.
Won't the what?
Nothing.
Okay. So I have a fraction, right? It's made up of a numerator and denominator, so I look at each piece. Look at the denominator, x squared. It's always positive. So the only way this is going to be negative is if the numerator is negative, right? So I've got to write down, if I want to know when f prime of x is less than 0, that occurs when 1 minus ln of x is less than 0. So if you move the ln of x to the other side of the inequality, that's when ln of x is greater than 1. So what value of x do I plug in to ln to get 1? ln of e is 1, right? ln of e is 1. So I need to make sure the ln of x function is definitely increasing. So I need to make sure x is bigger than e. Yeah.
What are we using again?
So I have this lower bound on ln of x, right? I'm saying, so I'm asking when is, hold on. What I'm asking is when is ln of x equal to 1? Well, when is that equal to 1? When x is e, right? So that's when it's equal to 1, but ln of x, if I graphed it, it's an increasing function. So in order to guarantee that this ln of x is bigger than 1, I need to make sure x is bigger than that value e. Okay? So 2 point something, right? So it's not technically decreasing at the beginning of my series, right? Because before I would see x needed to be greater than 1, but here it's x is greater than e, but it's okay that it's not decreasing for the first few terms. You just need to make sure it decreases after a certain point, okay? So this tells me after a certain point, so what I just learned is that f of x is decreasing on the interval e to infinity. So it's not 1 to infinity, but that's okay. So I have my 3 conditions: continuous, positive, decreasing. We can actually use the integral test now. Okay. Integrate from 1 to infinity, ln of x over x. And we need to compute this improper integral. Yep.
Why are we not integrating from e to infinity?
Because the bounds come from the ones that are on your series to begin with.
Oh,
Here and here. Yeah.
so are we really even going to be using the e?
No, we just needed to know that our function was decreasing after a certain point. So after e, my function decreases. But we don't need to know that specific value, no. All right, so now let's put in a limit, right, for an improper integral. We want to integrate ln of x over x. How do you do that? We saw these integrals before, right? Whenever we integrate, what's the easiest way to integrate? The substitution. That's always where I like to see if I can do that, right? Can we do a substitution here? Yeah, what would be my u? ln of x. Okay, great. So u is going to be ln of x, and du is 1 over x dx. So I can put this into my integral. U du. I just did a substitution on a definite integral. I have bounds. What's the thing you have to worry about? You have to change the bounds, right? So let's figure out what the new numbers are. So let's take and plug in, right, our original numbers in place of x. So u equals ln of 1. 0. So my new bottom number is 0. U equals ln of t. That's my new top number, ln of t. Okay. What do I get when I integrate u? U squared over 2? And then we're going to plug in our bounds here. Ln of t squared over 2 minus 0, so I'm not going to write that. And now we can calculate this limit. What's this limit going to be? What's happening to the numerator? As t goes to infinity, and the bottom is fixed, right? So this limit is going to be infinity.
But for 0, it does the same thing, right?
If you plug in 0 into this, you would get 0, right? So when I computed my improper integral, did it converge or diverge? Diverge. What does the integral test tell me then? The series also diverges. It has to go along with the integral. Whatever happens to the improper integral also happens to the series. So we just saw that when I computed this improper integral, this thing diverges. So what it does is now it tells me that my series ln of x over x, sorry, n, this should be n, ln of n over n, diverges by the integral test. Okay. Any questions?
We need to include by the integral test in our answer.
Yeah, because I want you to get in that habit now, because what's going to happen is we're going to learn a lot of tests. We're going to learn about alternating series test and ratio test and all of those different methods. And so on your test, you're going to have to say in your answer, the series converges or diverges, and then you're going to have to say which test you used. So I just want you to get in the habit of writing down the test every time. Yes. Yeah.
Will the answers be different for each test?
Will the answers, you mean the diverging and converging part? Yeah, there's different, the tests work differently. They have different things, different hypotheses. Like for the integral test, I have to show that my function is positive, continuous, and decreasing. You don't have that in the other tests. There are different things that are going on in different tests. Yeah.